Okay, now let's talk about let's do an example. An example is 10.2, and it is related to voltage reduction parameter we studied in the previous slide. It says a certain amplifier has a mid-range RMS output voltage of 10 volts, right? So I can write the given data that V out over here is equal to 10 volts, right? So if this is 10 volts, what is the RMS output voltage for each of the following dB gain reductions, okay, with a constant RMS input voltage? So it says that what would happen to this output voltage if the gain is reduced by 3 dBs, by 6 dBs, by 12 dBs. So first of all, we say we should have to solve this one. So basically we want to calculate or estimate the ratio, the voltage ratio which is associated with this reduction value, okay. So again I repeat, so you want to calculate a certain ratio, okay, which corresponds to this minus 3 dBs, okay. So when we compute that ratio, so basically we can see, we would say that okay, 10 times, okay, that ratio, okay, would be would give us the change in the voltage, okay. And similarly for part B, for part C, and for part D. So for that case, what we do, by definition, if you see this minus 3 dB, okay, this minus 3 dB is equal to you remember that this minus 3 dB, okay, it is basically what this is. By definition, it is a voltage gain. So this was 20, okay, log of AV, right? This will, so over here I can say that if I want to find the corresponding ratio, okay, which is voltage gain ratio, so it means that I need to have minus 3 divided by this 20, and then I need to find, okay, the anti-log of this anti-log, okay, the anti-log of this ratio. So if I do like this, so basically I would get this AV, and then I can put this over here. So I will get a reduction in the voltage gain. So for that, what can I do? I go there, right, okay, and I can see I can calculate the value. So this is minus 3 divided by minus 3, this is division, divided by 20, okay. So this comes out to be 0.5. I'm taking the anti-log. Anti-log is this. So if I take the anti-log, so the ratio is 0.707. So the value is 0.707. So I can write over here, sorry, it gone. I can write over here this ratio is, okay, V out is equal to 10. The new value of V out will be 10 times 0.707, okay. So it comes out to be, and it is written over here, how much? This is 7.07. So the output voltage, which was initially equal to 10 volts, is now reduced to 7 volts. So similarly, you can repeat the same procedure for 6 dBs, for minus 12 dBs, and minus 24 dBs. Now next in the slide is, okay, next in the slide is that for a low frequency amplifier response, if this is the circuit, okay, so this is just again a recap of what we have done. So it says, let's go through the slide. Now it says that if this is a common emitter amplifier, okay, now because of the low frequency response, right, okay, if frequency is decreased, this frequency is decreased, so XC would decrease, oh sorry, if frequency, low frequency, so we should talk about decrease in frequency. So if frequency is decreased, okay, so we have an increase in the reactance of the capacitor. So basically it says that there will be formation of this would result a non-zero value of the capacitance, okay, of the reactance. And because of this, okay, we would have significant reactance over here, okay, in this path over here, and in the over here in C2. So because of this significant capacitance, okay, you would have formation of three RC circuits, okay. One RC circuit is formed by the input coupling capacitor C1 and the input resistance of the amplifier. So one RC is basically over here. This is your first RC. The second RC is formed by the output coupling capacitor C3 over here, okay. So I can denote it, this is okay. So this, there will be another, this is C, okay, not RC circuit, RC. So this is the second RC would be formed because of the coupling capacitor C3, and similarly the third would formed by the emitter bypass circuit, which is given over here in this direction over here. So there will be the formation of three RC circuits, right? Okay, now over here if you see, so now this is this slide basically shows that how we can simplify our circuit when RC circuits are formed. So over here what we assume, actually we assumed only the formation of RC circuit at the input at this part, okay, and in this study, in this lecture, so we can ignore this RC, I can ignore this RC for time being, okay, and I can ignore this RC for time being, okay, this over here and over here. So it means that the only effective RC I am taking as a case study is at the input. So basically if I draw a line like this, so I would take this part into consideration, I am not taking this into consideration. So if this is the case, so I can, what I can do over here, okay, now this part is the equivalent circuit of this input of this branch of this, okay, this circuit of this portion. So we can see this is C1, so C1 is over here, and if you see I can replace okay, this R1 and R2, okay, over here R1 and R2, okay, with another resistance, okay, I can combine this R1 and R2 with another resistance which is known as R in base. And we remember we studied that this amplifier, okay, this can be represented by its equivalent resistance, and that is known as R in, okay, and R in at the base, R in B. And remember it was do you remember it was for this circuit, we can say this is beta AC, okay, R E prime, okay, R E prime. So it means that this, okay, so this is the equivalent, this is R in, this is the equivalent resistance of amplifier, and then another resistance which is R1 R parallel to R2. So I can add the base, right, okay. So I would have a resultant resistance which is a parallel combination of these three resistances, and C1 is as it is. So if you see, this is what this is, an effective RC circuit. RC, this whole is an effective RC circuit. Now thank you.